Ladies and gentlemen, welcome back. Today we're working on a Kenmore stove board. This is out of a 970C series. And it's got the same problem that all these Electrolux power boards seem to have lately, and that is a burned up resistor. This board came to me with the entire front panel. So there's a display and a bunch of buttons here. There is a clear adhesive we're trying to keep clean, so that's why the tape is on top there. As you can see, the guy did a pretty good job of keeping the junk out of it. So we'll just cover that back up. It's got a couple little spring clips there holding this board in, and then there's a pin connector. You got to be careful when you pull this out. So I doubt there's anything wrong with the display board, but yeah, and the engineers in there. Lovely zip tie. So here you can see the smoke trace. I guess you know which way was up in the unit. It's quite the amount of spore from one resistor. So you can see that trace there got a little warm. The solder joint got hot too. And I'll just rip the relays off the board here and get some access. There you can see all that mess. It's on the white relays there too. So we'll get this cleaned up as best we can and see how. I suspect not all this soot is going to come off. I don't know how long the resistor was burning for, but it could have been several minutes, and it burnt the fiberglass board a little bit too. I could take a Dremel and clean this all out of there. But like I said in the last video, that had a similar problem. By the time you got through all the burnt material, you'd have a hole left in your board. And there's traces underneath, so best just to leave it. I'm scrubbing everything that's coming off the board loose there, scrubbing it quite hard with a Q-tip. Now we'll take a look at these relays. Well, first the resistor. That's all that's left of it. There's no way you're getting color codes off of that. But they seem to be all the same as the other boards, so probably a 231 ohm. Just checking this trace here. It looks okay. It looks like the solder resist mask just got a little hot there. The copper seems fine. Scrape it away and I'm getting clean copper underneath. Just making sure all these still connect. I'll get this soot off the relay so we can see how bad they are. This one's got some heat marks. That plastic got hot, but it didn't distort particularly, so as long as it works electrically, I'm just going to leave both of these relays in here. Just a beauty mark. So just to prove that what's left on the board is not conductive there, I'm putting the leads very close together and I'm not getting any reading whatsoever on the. I think this meter goes to 20 mega ohms, might even be higher than that. So the leads you see to the right come from a power supply. I have it set to 12 volts, so we're just making sure all the relay contacts work here. That's the normally closed there. That meter beeps when there's conductivity. Just use the alligator clips to hold the meter on there, and we'll manually use the 12 volt probes to trip the coil. So the big one is good. Getting these clips on the tiny little leads is a chore, but and the small relay is good too, so Did not damage either of the relays, and damaged relays was not the cause of the problem on the board. So I'm just digging into my tickle trunk here with resistors. Based on how this resistor is used in the circuit, I'm not too worried about getting exact value. I'm pretty sure it was a 231 ohm resistor that came out of there, and the closest one I have is a 239 or a 240. So, given how it's used in the circuit, that's fine. If it was really like a measurement part of the circuit or something, I would, of course, be a little more fussy about getting the exact resistor measurement value. So now I'll just stick the relays back on the board. We will go over all these solder joints later on, just to make sure, especially the larger ones. Stuff moves around. One of the big problems with these boards is they're actually single layer boards, so there's not really very much strength to each solder joint. If you have double layer boards, usually the holes are all plated through, so they have the entire thickness of the board that bonds to the solder. But these, because they're just single layer boards, they only have copper on one side. There's just a thin membrane of solder. And some of these connectors get a huge amount of force. If you've ever tried to remove the plugs that go into this board after they've been on there for a while, it's very difficult to remove them, and it's easy to break pins or flex the board enough that other things break. It's not a very hardy design. Some of these pins here with huge traces, they take quite a bit to heat them up. So you'll notice I have quite a long dwell time on the solder, but I want to make sure everything gets melted together good and proper. So I'm just going to hook my leads back up here. Just want to see whether this relay has conductance when it's energized. Then we're going to take this 12 volt power supply here and see if we get that one conducts. So that relay is good. This is kind of the master, the main power in, and then each relay has its own power output plug here. So I'm just going to switch to the next relay in sequence. And all of these relays do conduct so far. So these three relays are good. That's your broil relay, your bake relay, and your convection relay. Okay, these leads here are hooked to a 5 volt power supply. Now what should happen, this is going directly to the main 12 volt rail for all the coils. So one side of every coil will be getting 12 volt positive. The controller feeds a 5 volt signal in this side of the chip, and in response the other side of the chip grounds the coils of one of these relays. So if we have our 12 volts, in this case I'm just going to use a 9 volt battery. We're going to simulate, this is 5 volts, we're going to simulate the controller telling the big relay to turn on. Probably have a proper clip for a 9 volt battery, but I just can't put my finger on it right now. So this is a little janky, but we'll make it work. So that, our 12 volt circuit is high. Now when I touch this with 5 volts, the relay should trip. Hear that? There's nothing wrong with the control circuitry for this relay. So there's nothing wrong with the control circuitry. We've seen that. All of these relays work properly. They all conduct. This one conducts just fine, conducts in the normally closed position, conducts in the normally open position, and the control works fine. If there's 5 volt input here from the microcontroller, it will trigger that relay. We manually did that. So, what is the problem on these boards? This transformer here provides enough power to trigger all the relays, so I'm guessing it's probably 10 or 20 watt power transformer. Just a guess. This is the primary side here. Let's see where it gets its power from. These two traces here are your power inputs for the primary. So this one here goes over to this lug here, which is your L1. So that'll be your black wire on the diagram. The other, this is the neutral side. You can't see under the, it runs right there. Okay, flip that over. That's that long, get this out of here. The long silver wire that runs down the side there. And it comes out right here. And then it continues around to here. So pin 1 on this jumper here is neutral. Okay, so that's where your power transformer gets its power from. Neutral here and your black line here. Notice this trace here. Right here, attached to this neutral trace, is our problem resistor. Problem resistor is right here, ends here, ends here. This is the normally closed, hang on, I'll get my meter going here so you can see. This is the normally closed contact of this big black relay, which is the main for both the broil and the bake elements. So if everything's working right, no relays are on, this ties your broil and bake elements, kind of pulls them gently to neutral through this resistor. Remember I said neutral comes in on pin 1 here of this jumper. Solder joint's broken. So a couple explanatory notes here. This is the circuit. This is the resistor that keeps blowing up. So how does this happen? Well, obviously power is flowing through here. Otherwise, nothing would happen. This resistor's purpose seems to be to connect these bake and broil elements to neutral when nothing is powered through this normally closed contact of K1. Should run through what relays are. K1 is the big resistor, the big relay here. Use your words. K3 is this one here. K5 is this one here. So it's marked broil, that one's marked bake. This is for your convection, that's a different circuit. So what happens is, in order for power to flow through this resistor at all, this relay has to be open in order for this contact to be closed, and it must be getting power from somewhere, which means one or both of these relays must be closed. The only source of power here is this line 1. So what is happening, what must be happening, is one or both of these relays is closed while this one is open. Now that's not normal circuit operation. So how is this happening? As we saw, before I go there, this solder joint, the solder joint rather here on J3, is breaking, meaning it's cutting this transformer off from power. Which means the entire DC rail for the power board, and this also runs the display. This transformer and its power supply runs the display in the entire front panel. What's happening when this neutral gets cut off here is your board power drops. So the voltage goes from 12 volts down to, who knows, 1 volt, 5 volts, lower than 12. When that happens, remember these relays, they're different sizes for one thing, and you'll never get relays that close and open at the exact same voltage. What's happening, if you, I did some experimenting. This is the voltage each of these relays drops out at. So you can see about 1.8 volts. But look at the voltage they pull in at. See the difference here? This is this little one here is a full volt lower than this one. So you could have the power supply voltage for the relay coils dropping, and it could be still high enough to keep all the relays closed. If it drops below 1.8 volts, all these relays drop out. 1.7, 1.8, somewhere in there. So at this point, I'll bring the schematic back here. Okay, we're going to focus on K3 and K1 because this is the biggest voltage difference here. Okay, so at this point, we haven't dropped below 1.8 volts yet. We're still above at some voltage. Voltage gets to 1.8 volts. Both K1 and K3 drop out briefly. Now the voltage rises back above 1.8, but remember it has to get to this voltage here before the relays close again. So it sputters around for a while. When it gets to 5.8, K3 will turn on, but we haven't got to 6.8 volts, so K1 won't turn on. So in that situation, we have the perfect storm. We have this relay open, so this is connected here. So we've got power flowing from, okay, K3 is closed, so we've got a power path from here through K3, through the broil element, through K1 normally closed, through the resistor to neutral. And that's why resistor 1 burns up. I don't get the point of resistor 1. If it's there as a safety thing to prevent somebody from getting a shock when they touch these elements, or whatever, I'm just guessing here. That's a 1/4 watt resistor. If you have anything, any form of power touch either of these elements, some fault, it takes nothing at all to overwhelm a 1/4 watt resistor, which is why it burns up, because there's a fault. So there's really no protection provided by R1 as far as shock goes. The only other reason I can think of that they would put that in there is to deliberately light the thing on fire if there's a problem, which there's better ways of alerting the consumer to a problem than your stove lighting on fire. So I don't understand why they would put that in there. If they just wanted to use to have a gentle pull to neutral, they could have used a resistor that's large enough that it wouldn't burn up if there was an actual fault, serious fault. For instance, probably a 100K resistor would survive exposure to 120 volts or 240. If it was there for some kind of voltage monitoring or current, if it was there for current monitoring rather, it would be a very, very low resistance. It would be in the milliohms. That's not the case. It's, what was it, 231 ohms, I believe, was the original one. So it's in this zone where it's going to burn up if anything happens, and it doesn't really do any good. So I'm not sure what the engineering was, the theory behind it, but anyway, this is the situation it's in. If that resistor wasn't there, I don't see why the circuit wouldn't function. The only thing it does is connect these elements to neutral when this relay's off. There's nothing else connected in the circuit. It doesn't appear to be there for monitoring. It must be just there for safety, and it doesn't provide any safety. So if that resistor was not in place, these boards would still go crazy because of the broken solder joints. The main board isn't getting power. It needs to carry on coherent thought. So things would still be bad, but at least it wouldn't light on fire. I can't be 100% dogmatic about that, and I don't like changing the design of boards that I'm working on. So I replaced the resistor, but that's, for what it's worth, my opinion on its value to the overall circuit. So I just do the two end ones separate so that the connector doesn't want to walk its way out of the board. Inspect the rest of the little solder joints you probably don't have to worry about, but it's the big ones. Okay, so that's everything in this area we've looked at. I'm also using a leaded solder, so it'll have a little more malleability. Hopefully doesn't crack as easy. I just touched everything up in that row. Yep, that solder joint was cracked. You can tell by the way it melted. Part of it melted, then there was a, up to that line, there was a pause, then the rest of it melted. Making sure none of the relays walked their way out of the board. This is there's a clear adhesive on the front of this panel. This, incidentally, is a good trick if you're trying to keep adhesive clean. This is the backing tape off of foil tape roll. And it's got some kind of, I don't know, Teflon. It sticks very slightly to adhesive. So the control panel checks out, has control of the oven. It'll give an F30 code, which means there's no temperature sensor connected. But you can hear the relays clicking and it seems good. So we're going to call that a fix. And thanks for watching.